Assalamualaikum and good evening. For CHM3303 Inorganic Chemistry 3 for experiment 6, my partner and I are going to present about the preparation and spectroscopic analysis of a copper glycinate complex. So for the learning outcomes is to describe how to synthesize a copper complex of a glycinate region. Second is to deduce the complex stoichiometry by spectrophotometric analysis. For the introduction of copper to glycinate, or in IUPAC name, bis-glycinatum copper 2, it refers to the coordination complex of copper 2 with two equivalents of glycinate with the formula Cu glycinate 2 with monohydrate, where X is equals to 1 monohydrate or 0, which is copper to glycinate in anhydrous form. All complexes of copper to glycinate will take form of blue colored solid. Below is shown the color of the copper to glycinate as well as the structure of the compound. The glycinate forms a 5-membered chelate ring with the glycinated ligand serving as a bidentate K2O species, and the chelating ligands assume a square planar configuration around the copper atom as is common for tetracoordinate E9 complex. So, for information, the glycine is actually the simplest amino acid that has a single hydrogen atom as its side chain. You can refer to the diagram on the right side of the presentation. So next, the direct reaction of copper to acetate, monohydrate, and glycine results in an equilibrium mixture of two isomers product. So if we look at the upper part of the slide, we react copper to acetate, monohydrate with glycine, and we produce two possible geometric form isomers as cis and trans. So the glycine ion is not symmetric. So the structural isomers can depend on the relative orientation of the ligands. Because of the unsymmetric nature of the ligand, the square planar coordination thus give rise to two possible geometric isomers, the cis and trans form. You can see on the right side of the slides the cis structure as well as the trans form of the copper to glycinate monohydrate. There are multiple ways of differentiating the geometric isomers. For example, the IR spectroscopy with the characteristic number of C bond N, C bond O as well as Cu cuprom 2 bond N that will identify the ligand configuration. Crystal appearance may also be some value for isomer indication, although the ultimate diagnostic technique is the X-ray crystallography. Okay. This is the synthesis of copper to glycinate monohydrate. First, we weigh 2 grams of copper acetate monohydrate. Then we transfer the solid to 125 ml Erlenmeyer flux, which we will label as A. Then we weigh the empty bottle. Don't worry if not all the solid are transferred into the flux. You can just calculate the exact amount of solid transferred by using the weight difference. Next, in the flask A, add 20 ml of distilled water and wash down any solid remaining in the funnel. Stir the solution using a glass rod. Then we repeat step 1 until 5 with 1.4 gram of glycine into flask B. And a third flask was prepared by filling it with 20 ml of distilled water. So the next step is to place the flasks on a hot plate and begin heating them slowly until it simmers. We Stir the flux A and B occasionally to ensure that all of the solids dissolve. After the flux are heated until simmer, remove the flux A, B as well as the third flux from the burner and rinse the glass rod in flux B before removing it. Next, we transfer the content of flux A into B while the solution is still warm. Make sure to rinse the glass rod as well as the funnel to ensure the complete transfer of the solution. Then we allow the mixture to cool for a few minutes. While waiting for the solution to cool, on the other hand, we can prepare an ice bath. Once the reaction mixture cools down until room temperature, place the flask into the ice bath. And after some time, crystal precipitate will begin to form in the reaction mixture. But if the products are not precipitated out, there are two techniques to encourage precipitation. Next. The first technique is to scratch the inside of the flux gently using a glass rod in an up and down motion. The second technique is to obtain a small amount of product and add it into the solution. The crystal will act as a template for the dissolved product to begin their precipitation. Upon crystal formation in the flask, we must add 20 ml of acetone or ethanol. Make sure to stir the solution continuously and allow it to cool for a few minutes in the ice bath. Next, we must set up the vacuum filtration. We also must ensure that the tube is deep and attached securely to the vacuum outlet. Use a few milliliters of acetone or ethanol to wet the filter paper before the product transfer. This will ensure that a seal between the product and filter paper and prevent the product from draining into the funnel. Next. The next step is to transfer the product into the vaginal funnel using a spatula. Then we use a few milliliters of cold ethanol to rinse out all the precipitate in the Erlenmeyer flux. We will allow the product to dry thoroughly in the vaginal funnel. Pre-weight a plastic bag and record the weight. We make sure the product are dried thoroughly in the vaginal funnel. And lastly is to detach the tubing from the outlet before turning off the vacuum pump. Next. Once the dried product is carefully transferred into the pre-weight bag, make sure to do this by placing the bag into the beaker and transfer the dried product using a spatula. Once we have finished transferring the dried product, close the bag securely from the top. The last step is to weigh the bag as well as the product, and we must calculate the product's weight by taking the difference between the two readings. There are several precautions that are not mentioned in the video. First is when using the measuring cylinder, the volume of the liquid should be read from the base of the meniscus. When using the vaginal funnel, make sure to use a steering rod to filter the solution down, not the side of the beaker to avoid spillage. Lastly, the experiment must be done in the fume hood, which will reduce or eliminate exposure to volatile liquid, dust, and mist. From the second video is the preparation of CuCl4 from a Cu2 plus complex for UV analysis. Hexa-alpha-cuprate 2 ions contain a Cu2 plus ion as well as 6 water molecules that will act as ligands. The compound will form coordinate bonds by donating a lone pair of electrons. This will give the solution a pale blue color. You can see on the two diagrams is the structure of the complex as well as its color. From the equation, we can see how hexa-aquacuprate ion will react with chlorine ion to produce CuCl4 as well as 6 molecules of water. So the chloride ions ligand will substitute the water ligands to form a tetrachlorocuprate 2 ion. This will give the solution a yellow color. So although it appears green in the video, it's required that the color to be given as yellow. So finally, the shape of the complex ion will change from octahedral form to tetrahedral geometry. You can see from the diagram is the structure of the tetrachlorocuprate 2 ion as well as the color which is yellow. Next is the UV-based experimental procedure. The apparatus is solvent bottle, a waste beaker, the sample solution that we are going to experiment, as well as a pair of cuvette. The cuvette can either be made of plastic, glass, or quartz. Next. So first, we must do a blank solution scan for both the reference and the sample, which will contain the solvent only. Next, we must rinse the cuvette with the solvents that are being used. Shake and dispose it in the waste beaker, and it must be repeated 2 times. The third step is to clean the transparent sides to make sure that no fingerprints, grease, paperlines, or droplets are on the clear side. This is because the light will pass through the transparent side, and we do not want the light rays being refracted. Next is to insert the cuvette in which the transparent side in the east-west direction, where the light will come. The fifth step is to place the 2 cuvettes into the blank and sample holders accordingly. We can close the lid and do the auto zeroing. Next. In this instrument, you must press button 2 to access the spectrum. So our range is around 800 nanometer to 400 nanometer. So our absorbance will be around 0 to 1.5. So and lastly, press auto zero. Next is to take out the sample cuvette and rinse it with the sample solution multiple times. We must not let the solvent's remnants to dilute and affect the result. Number 9 is to pour the sample into the cuvette and rinse it with the sample used and dispose it, and it must be repeated 2 times. Next, we fill the cuvette to 4 or 5 of height with the solution. Make sure to clean the transparent sides and place it into the sample holder. On the button, you must press start. We can to zoom, just press F1 and F3 to auto scale. Next is to press F2 for data processing and press button 3 to see the wavelength and max absorption of the spectrum. Lastly, we must press F2 to print the spectrum into the paper. Next, I will pass on to Jaslyn.
Okay, so the next is the use of the standard curve. So the standard curve are graphs of light absorbance versus solution concentration, which can be used to figure out the solute concentration in the complex. So a spectrophotometer measures light quantity. It tells how much light is passing through a solution transmittance and how much light is being absorbed by a solution adsorbance. So when the sample is placed in a spectrophotometer, it will show the absorbance of the solution through the graph. And we notice that as the concentration increases, absorbance increase as well. So we can estimate the concentration of an unknown from just looking at the graph. A more accurate way to determine concentration to actually use the equation of the line which fits to our data points. So we can use the equation y equals to mx plus c. As translated as here, y is the absorbance, so m is the slope, x is the concentration, and the y-intercept is absorbance value. Next, the slope and the y-intercept are provided when the computer fits a line to the standard curve data. The absorbance, or y, is what we measure from the unknown. So next, for the example, the unknown's absorbance y is 6. We can see here is 6, and based on the curve below, the slope m is equals to 8 and c equals to 0. So when we use y equals to mx plus c, then 6 equals to 8 times x plus 0. So we get the x value is 0.75. So the concentration of the unknown would be 75% from the original stock, which was 100 milligram per mil. 75% of 100 milligram per mil equals to 75 milligram per mil concentration. So next is how to determine the error of the standard curve. So to understand the error, the response at each concentration can be repeated so an error bar is obtained. Next, the data are then fed with a function so that unknown concentrations can be predicted. Next, typically the response is linear. However, a curve can be made with other functions as long as the function is known. The calibration curve can be used to calculate the limit of detection and limit of quantitation. So the concentration of the unknown will have some error, which can be calculated from the formula below. So m is the slope of the line, b is the y-intercept, b or c we use is the y-intercept of the line, n is the number of standards, k is the number of replicate unknowns, y unknown is the measurement of the unknown, y bar is the average measurement of the standards, xi are the concentrations of the standards, x bar is the average concentration of the standards. So that's all from us. Thank you. For now, we'll proceed to Kahoot session.